Hello everyone, I'm Dr. Fawzul Atiq, giving some series of lecture for the course Discrete Mathematics. So we are at the graph theory unit and we have done the basic introductions of the graph. And today, the first part, we'll discuss about how to represent the graph and then the isomorphism of graph. Okay, now to represent a graph, like we have learned, graph is something which is having vertex, which is having edges, all these things. Now that suppose I have a graph. I have some graph and it is looking like this, suppose. So the vertex name is A, B, C, D, E, F. Like this, I have a graph. Now, this graph, I can see that, and I can see that, okay, there is no edge between A and F. There is an edge between A and D. All these things are there that I can see. But how you represent the graph to the computer, right? Or how you can represent the graph mathematically without drawing it. It is possible, right? So one of the easiest and the first method is the adjacency matrix and adjacency list, right? There are two methods, but there are many other ways, many other matrices are also there. But what is the adjacency matrix? Many of you may know it, those who have done the data structure algorithm course. So it is the matrix is, it's an, suppose I have a 6 vertices graph, so I'll have a matrix of order 6 by 6. So a matrix A I'll have of 6 by 6 order, whose rows and columns are indexed by the vertices of this graph. So it is A, B, C, D, E, and F. Like this, the rows and vertices are indexed. Similarly, A, B, C, D, E, and F. Now, how you can fill the matrix? Now, from A to A, there is no edge in the from A to A, so it is 0. A to B, there is an edge, so it is 1. A to C, there is no edge, so 0. A to D, there is an edge, so 1. A to E, no edge, 0. A to F, no edge, 0. So this is how you can fill the matrix. Similarly, B to A, there is an edge. B to B, no edge. B to C, there is an edge, 1. B to D, there is no edge. B to E, there is an edge, 1. B to E, there is B to D, there is no edge, sorry, it is 0. B to E, it is 1. And B to F, it is 0. Like that, you can define. And one more thing, that because A, whatever things are there, A is adjacent to B, because it's an undirected graph, A is adjacent to B means B is also adjacent to A. So this matrix is actually a symmetric matrix. So I don't have to do the whole matrix. Whenever I have done the first row, I can immediately fill in the first column. The same thing will happen. So 0, 1, 0, 1, 0, 0. How I have checked? I check the first row. Similarly, I check the first row. It is this one. So the same thing will happen in first column. Correct? Similarly, for the second row, it will become the second column. Right? So I'll do it in that way. So second row will be 1, sorry, B to B, it was 0. So B to B, it was 0. Yes, so B to B has 3 degree, and then B to A, there is 1, and B to C, it is 1. Sorry, it was missed. Correct. So now the second row is this. The second column will also follow the same. So 1, 0, then 1, 0, 1, 0. Similarly, C to C, 0, C to D. C to D, it is 1. C to E, it is 0. C to F, it is again 0. So 0, 1, 0, 0. Same thing will follow. D to D, 0. D to E. D to E, it is 1. D to F, it is 0. Similarly, 1, 0. This is 0. E to F, 1, 1, 0. This is how one can fill the matrix. Similarly, adjacency list, all of you know it mostly, but I'm just for your recall purpose. Adjacency list is what? It is also a tabular form. So some in one place you will have the vertices and the list of their adjacent vertices. It is vertices and it is adjacent vertices. Adjacent vertices. So what are the vertices? A, B, C, D, E, and F. What are the vertices adjacent to A? Maybe I can make some tabular form so that it will be easy to see that. And okay, A is adjacent to whom? It is on B and D. So B and D will be there. B is adjacent to whom? It is A, C, and E. C is adjacent to B and D. right? And then D is adjacent to, it is A, C, and E. E is adjacent to D and F. Okay, B, D, and F. B, D, and F. And F is adjacent to only E. This is how you can do it, right? So easy thing. So you can represent a graph by using this. Now, similarly, one can also draw a graph from the given adjacency matrix. So what you will do, the same thing, like suppose you have this matrix with you, and you just have to draw the graph of it. You have to draw the graph of it. Or maybe I'll draw a small adjacency matrix and let us see. I'm drawing a matrix is given. Suppose 0, 1, 0. Small I'm doing. Then 1, 0, 1 I'm doing. And then 0, 1, 0. So I have a matrix. It's an adjacency matrix. Can I draw the graph? Yes, because it's a 3 by 3 matrix. So I'll make some vertex name, maybe A, B, C, A, B, C. Right? So I'll have a 3 vertices in the graph. One is A, B, and C. Now check the matrix. A to A, there is no edge. A to B, there is an edge. So fix this edge. A to C, no edge. Then B to A already done. B to C, there is an edge. Fix this one. And C done. And C to B, there is an edge done. So this matrix I had, from there I make this graph. Right? Similarly, that one can draw a pseudograph from the given adjacency matrix. Pseudograph means where these things are there, where your somewhere you can involve the, which is not a, may not be a simple graph, right? You may have, maybe I am doing the same 0 1 0 1 1 0 and 0, sorry, 1 1 0. Okay, 1 1 1 I should do, or that is also fine. And 0, just a second. So 0 1 1 I'm doing, and then this is 0 1, and again 1 I'm doing. Correct? Or maybe this one is 2, suppose. Then I have to draw a pseudograph from there. This is also 2. Now A, B, C, A, B, C. And how to draw the graph? There will be 3 vertices, A, B, and C. Right? And then A to B, there is an edge. A to C, no edge. B to A is already there. B to B. So therefore, there should be a loop, because B to B it is 1 and B to C it is 2. So there will be 2 edges from B to C. Right? Then C to B already done, and C to C there is an edge. So this is how this pseudograph will look like from this given adjacency matrix. So this is the adjacency matrix was given, and you got this graph. Like here, the question was drawing a pseudograph from a given adjacency matrix. So matrix was given, you have drawn the pseudograph. Similarly, if the pseudograph is given, you can find the matrix. Right? So these are something that you can think of it. Now, I am interested about the isomorphism of a graph. Now, what is isomorphism? First, let us understand that. I am drawing some graph. I am drawing a graph, this one. Yes, I am drawing this graph. Now, if you have gone through the previous slides, which graph it is, all of you know, because it is a C4 graph, cycle graph C4. And sometimes some students say it is a square graph. Those who don't know the terminology of graph theory, they say it is a square graph. But I said it is not a square graph. In graph theory, there is no that kind of square term in the graph theory. It is a cycle graph C4, right? Although it does not look like a round shape, but it is a cycle graph. Now, this graph, one can also draw it in this way, right? So it looks like a square now, it is looked like a rectangle, right? But it is still a cycle graph C4, because it's 4 vertices, 4 edges, and they are connected by a kind of a ring. So it is C4. I am drawing another graph, maybe this one, this one, this one, and this one. This is still a cycle graph C4, although it does not look like a rectangle or square. It's like you twisted the rectangle, but it is the cycle graph C4. Right. So all these things I just have represented differently, but they are the same graph. All properties are same for all three graphs. So in terminology, the graph theory terminology, we call them as isomorphic graph. we call them as isomorphic graph. And isomorphic means there is an isomorphism between them. What is an isomorphism? So two simple graph G1 and G2 with vertex at V1 E1 and vertex and edge at V1 E1, and in G2 V2 and E2 are isomorphic if there exists an one-to-one and on-to function. That means there exists a bijective function from the set V1 to the set V2 with the property that A and B are adjacent in G1 if and only if A and FB are adjacent in G2. Right? For all AB in the vertices V1. So nothing to worry. I'm just making some vertices here. Let us understand through this example A, B, C, D. And I have uh, mm, some name, maybe 1, 2, 3, 4. And I want to check that this two graph, first graph and the third graphs are isomorphic. What I have to do, I have to find a bijective function from the vertex set of the first set to the vertex set of the second set. Vertex set of the first set is what? A, B, C, D. To the second set is 1, 2, 3, and 4. Right? So this is a function, and this function should be bijective. Bijective means 1, 1, and on 2. And it should maintain the adjacency relationship. So find out which vertex looks like what. So f of A, if I'm taking it 1, what is f of B? So 1, so you have to maintain the adjacency relationship with same also. So 1 is here, but B is look like 3. So it is 3 here, right? F of C is what? C is adjacent to both A and it is adjacent to B, but not in A. B is adjacent to B, not so f of C looks like 2 here. And f of D is what? F of D is actually 4 in this case. Right? Now you see A and B are adjacent, and A and B are adjacent in the graph G1, and FA and FB, which is 1 and 3, are adjacent in the graph G2. So this function is also maintaining the adjacency relationship. Similarly, A and C are not adjacent in G1. A and C are not adjacent. And A and C, FA and FC, which is 1 and 2, are not adjacent in this graph. These two vertices are not adjacent to each other, right? So this is the adjacency relationship. So the graph, the function is bijective as well as it is preserving the adjacency relationship. Now, if you can this kind of function between two graphs, you call the graphs are isomorphic to each other. Otherwise, they are not isomorphic. Right? So I hope you understand this concept that isomorphism meaning. And if you get one property which is not satisfied, that which is there in one graph and not there in another graph, if you get one single property, you can immediately declare that the graphs are not isomorphic. Is it clear? I hope you understand. Similarly, like you can create something. I'm giving some more example. Maybe I'm giving an example of this graph. You check whether these two graphs are isomorphic or not. So I have drawn one graph. I'm giving one more graph. I'm giving one more graph and check whether these two graphs are isomorphic or not. Yes, these graphs are isomorphic. Again, although they looks like different, right? It is look like a pyramid and this like is a just a complete graph, but both the graphs are complete graph. You can certainly make an isomorphism. You can certainly make a 1 1 and onto function which preserves the adjacency relationship. You can certainly create that, na? A, B, C, D, and maybe you can put it as 1, 2, 3, and 4. Then you just define the function. Your job is done. So these two graphs are isomorphic, right? I'm giving one more example. You check whether these two graphs are isomorphic or not. See, if they are isomorphic, all property will satisfy. Her number of vertices, number of edges, number of cycle, bipartiteness, completeness, everything, connectedness, everything will satisfy, right? So I'm giving some example. You can check and tell me whether these graphs are isomorphic or not. Okay, I'm giving one more example. Check these two graphs. This one, and so these two graphs are isomorphic. This is G1 and this is G2. This is G1 and G2. So G1 isomorphic to G2. These two graphs are isomorphic. I am giving two more graphs here. So this is maybe G3 and G4. Can you tell me whether these two graphs are isomorphic or not? Even G3 and G4 are isomorphic. Correct? You can certainly make a isomorphism function, that the bijective function, which preserves the adjacency. Okay, I'm giving one more example, and you tell me whether these two graphs are isomorphic or not. Can you tell me these two graphs are isomorphic or not? See, both the graphs have same number of vertices, both the graphs have same number of edges, but do they isomorphic? No, they are not isomorphic. Why? Because these two graphs are not even, this graph is connected graph A, B, C, D, E, and F. And this graph is not at all a connected graph even. 1, 2, 3, 4, 5, and 6. So you can reach from, in the first graph, maybe this is a G5 graph and this is a G6 graph. In G5, you can reach from one vertex to another vertex. Any path. There are a lot of paths are there. Right? There are two paths are there between each pair of vertices. But from this graph in G6, from 1 to 2, you cannot reach. There is no path in this. Right? So whereas in the G6, you have a C3. This is basically union of two graphs, C3 and C3. Whereas G5 is a C6 graph. So the graph G5 and G6 are not isomorphic. They are not isomorphic. Clear? So prove it not isomorphic, you just have to give one property that these are not satisfied. You can immediately declare the graphs are not isomorphic. Okay, I'm giving one more set of example. Maybe this one I will do it in this way. Okay, just a second. You will have to look into it and tell me whether these are isomorphic or not. So I am drawing it. Another graph. So can you tell me whether these two graphs are isomorphic or not? This is the graph maybe now G7. This is the graph G8. Are these two graphs G7 and G8 are isomorphic? Look at it, observe it carefully. Actually, they are not. Right? Why? So you check that these two graphs, like here, you have a big cycle, like 1, 2, 3, 4, 5, 6, 7, 8. A cycle of length 8 you have. Whereas in this graph, you do not have such big cycle. Right? You do not have this much big cycle in the next graph, G8. So you can declare that these two graphs are not isomorphic. Although they have many properties are same. Number of vertices, number of edges, and the degree sequence. Even the degree sequence also they are same, but the graphs are not isomorphic. Degree sequence means the degrees of the vertices. Here in this graph also G5 and G6, the degrees are same even. All of them have the same degree, but the graphs are not isomorphic. Clear? So this way you can define whether the graphs are not if the graphs are isomorphic, you have to define the function, and if the graphs are not isomorphic, you have to give a reason that okay, this property is there in the graph, which is not there in the other graph, which is not there in the other graph. So this graph G7 and G8 are not isomorphic. Clear? So I'm done with this. So this is the all the content I have taken from this book only, Kenneth A's Rosen book. And I'm done with this. I am wishing you all the best for your final exam or for your exam. And I hope this course is helpful for you. And I'll come up with new videos in another lecture. Thank you very much.